Hi guys, we are going to be working on heating and cooling curves. So just a continuation of our phase change unit and our last big topic that's going to be on this unit test. So when we're looking at these, you're going to see that you're going to have a graph that's involving time and temperature. So the time is down here on the X, and then temperature is going to be going up on our Y. And just remember with temperature that this is your average kinetic energy. Over here on our y-axis, which really is measuring how fast the particles are moving. So we're going to be looking at each line segment. So I'm going to be using kind of some different colors just to help us with that. So my first line segment is going to start at A, and I'm looking at it going to point B. So because we're looking at all three phase changes in this particular heating curve, this is going to be representing our solid. So we have a substance that's a solid. So in this part here, we're simply just heating up the solid. It's staying a solid the whole way through. So there's only that one phase present. So some things that we could be asked about is how long is it in the solid form? What's going on with the particles? So a few things about a solid is going to be that from A to B, the average kinetic energy is increasing. Okay, and that's because temperature is increasing. And then we also, when we talk about potential energy is only going to change during a phase change. So for right now, just fill in, this will make a little bit more sense soon, that potential energy is constant. Okay, so that's from that A to B point. And we'll be adding in some other information kind of as we go. When we get to point B, and we see the line flatten out, what we know from A to B is that so from B to C, that line segment, okay, temperature is the same. Okay, so what must be going on? Why is it staying flat? And that's because in this case, we have our phase change. Okay, so from B to C, we are going from a solid to a liquid. Okay, both particles in solid and liquid are present. So in this case, this would represent melting. Okay, so if temperature is staying the same, what must be changing that's causing this phase change? And that's going to be because while temperature is staying the same, which means that our average kinetic energy is constant, it is the potential energy that is increasing. Okay, which is resulting in that phase change. Okay, so we have both solid and liquid present, it's melting. Okay, average kinetic energy, which is temperature, is staying constant, but it's that potential energy that is increasing. All right, when we hit point C, we'll see that the temperature starts to go up to D. Okay, at this point, it is completely melted and it is purely in the liquid phase. Okay, and we just have a liquid that's heating up. So our temperature, which is our average kinetic energy, is increasing again. But the potential energy, because there is no phase change, is constant. We're staying the same. All right, well, when we hit point D, we see that that temperature now flattens out again over time, even though we're still adding heat to it. So from D to E, we can see that we're at the same temperature. Okay, so once again, this is temperature, which means our average kinetic energy is the same. Constant. But we're adding heat to it, so something must be changing. And that's because our potential energy is increasing because we have a phase change. Okay, that liquid is going to be vaporizing or boiling, okay, and changing into a gas. So we have both liquid and gas particles present the whole time from point D to point E. And then finally, once we've reached point E, at this point, the line segment keeps going up to F. That means we are fully in the gas phase. And the same things apply as the solid and the liquid. Your average kinetic energy is increasing. Potential energy, because there's no phase change, is just constant. Okay. Two other big things that you can tell based off of this will be your melting point and your boiling point. So if we were to have a scale over here on the temperature, if we were to extend this BC line segment, okay, that would give us our melting point. And if we were to extend over, that's not very straight, but if you could actually make that level and you would have a scale if you were doing this, that temperature where we have that boiling occurring is going to give us a temperature of the boiling point. Okay, so we can ask a lot of questions about just different segments of what's going on with energies, what's going on with phases or phase changes, and then what's the melting point and the boiling point. I did want to show you on the other side of your notes a cooling curve. So for a cooling curve of a substance, we're going to see overall that the temperature is going down. So we're cooling it. So it's basically just going to be the reverse. So in this case, we're going to be starting with a gas that would be at the highest temperature. Okay, then you should be able to predict that, okay, at this 2-minute mark, I'm then going to be condensing. So this is condensing that's occurring. Okay, I have both a gas and a liquid present as it goes from that gas to that liquid. When I hit the 6-minute mark, you're going to see here from 6 minutes to 11 minutes, it's going to be just in a liquid phase. Okay, the temperature is decreasing for that liquid. When we get to 11 minutes, we see the temperature flatten out again. Okay, that would be where it's freezing. Okay, where we have a liquid changing into a solid phase. And then finally, after you get to freezing, if the temperature starts to drop, that must mean that it's completely in the solid phase. Okay, so some things that we can also tell based on this is where this flat peak is. Okay, the boiling point, which is the same thing as this temperature it's condensing at, for this substance would be 150 degrees Celsius, okay, just based on that temperature. Okay, I could also tell about this substance, the freezing and melting point. Remember, those two things are the same thing. Okay, where that line is, which is at 90, that would be its freezing point and its melting point at 90 degrees Celsius. Okay, again, we can also tell a couple things about potential energy and kinetic energy. Okay, and any of these line segments here, kinetic energy is going to be going down. Okay, on those three. And then what's happening during condensing and freezing? Well, that's because the potential energy is decreasing, which is causing that phase change. Okay. All right, so this is just some initial information to get you started. You're going to be doing a whole bunch of activities just to practice this and go through everything that you need.